Hello, calculus. So half of you probably have already gotten emails from me because you're in physics. But I am going to try for our e-learning. We'll try a few different things. So one of the things that, sorry, you can see I'm like in sweats. It's 11 p.m. One of the things that I'm gonna do with my other classes, we kind of built a board in my basement. That's what this is happening right now. And I'm gonna work problems out on this board and upload them to YouTube. So you'll have a series of videos of my lectures that would go with different sections in the textbook. So I'm organizing this a little differently than I said even last week. So for you guys, I'm sorry, this is so much transition, getting used to me and now getting used to me online. But since we're going to be splitting lessons up so much and meeting virtually for the foreseeable future, I am just going to split PowerPoints and then my lecture notes that I'll put on YouTube up into what would be appropriate for each day that we meet virtually. And I'll have assignments that go with that. So we'll see how it goes. If it gets too confusing, we can try some other things. We can also talk about trying Screencast-O-Matic if that works better for you. But let's see how this goes for now. So we're going to start chapter 3, which is applications of differentiation. So last week when I jumped into the class, we basically spent the week reviewing derivatives and all the different methods of taking derivatives. So I tried to organize that into those 2 PowerPoints you have. Feels like a lifetime ago, but from last week, with all the different rules like product rule, quotient rule, the chain rules, all those kinds of things. And so this chapter is pretty long, and we're going to really slow it down, obviously, because it's all new. And we are going to get into how we can use differentiation in some more realistic problems. So the first section, I'm going to kind of you'll see me coming over the computer because I'm going to try and follow the PowerPoint that I'll post to go along with this. The first section is about finding extreme, or they call them critical points, on a graph or for a function. So if you have a function, there are some important points to find. Essentially what we're going to focus on today is the maximum point. I'll throw out a bunch of different terms for this, but the maximum point and the minimum point. And when we start to get into the problems, which will not be in this video, but when we start to get into some of the more real life problems, you will definitely see, I hope, where this is applicable in the real world. But just think about, if you had a function like for a growth rate or for motion in my world or for energies, etc., it's important to know what your lowest point is and what your highest point is on an interval. So those are maximum and minimum. It's also often important to know the interval over which those values are increasing and decreasing. So for instance, right now, with everything going on, we are all hearing that the stock markets are on the slide. They're going up and down a lot, but they're on the overall decrease. And if people in economics, you're probably talking about that a lot. And you'll look at intervals over which it's on the down, so the decreasing or the upswing, and you would talk about lowest points or highest points over a certain given time period. So that's this kind of thing. Okay, so definitions. I'm really going to follow the textbook as we go. I really, really like your textbook anyways. But I talked to Ms. DePoe about how to handle this online stuff and just what she's doing with her AP class. And we both thought that using the textbook to guide us and avoiding any long derivations on the board would be the way to go. So I'm going to tell you that all of this stuff, I'm just following the textbook very linearly, section 3.1. And so the first thing they do is they define minimum and maximum. And you have those formal definitions for you on your PowerPoint. Basically, a point is a minimum if it is the lowest value over the interval at which you're looking or studying, and it's a maximum if it would be the highest value over the point at which you're studying. You also see the words extreme values used, extrema, absolute minimum, absolute maximum, global min, global max. They all mean the same thing. So basically minimum, maximum, right? And so we would say that if you are looking at a continuous interval on a closed, continuous function on a closed interval, then it would have both a minimum and a maximum. Now, your textbook shows some different examples. If a function is non-continuous or if it's on an open interval, there's possibilities that it either wouldn't have a minimum or wouldn't have a maximum. So you can see examples of that, but most functions that we will work with at the honors calculus level will have both a minimum and a maximum value. So we need to know how to find those. So to find those, you're going to use something called a critical point. Sorry, again, I'm just making sure I keep it up. And the critical points allow us to find these things. When you have functions, so if a function is graphed, let's say you even have, we're really not going to get too into the trig today, and yet I draw right away a sine function. Let me move out of the way. So if you can see this, there's kind of a glare. Let's see if I can move this closer. Come on, come on, come on, come on, come on. Is that better? Okay. So if you can look at this, if there are maximum values, they're basically what we would call the hills, right? And the minimum values are what we would call the valleys. So this would be a minimum value. These would be maximum values. And in the notes, you'll see that I refer to relative minimums and relative maximums. And those are on open intervals. So if you have a closed interval, then you're going to have an absolute maximum, absolute minimum. It's just a certain value that is the lowest point, certain value that is the highest point. If you have an open interval, then we would say that you have a relative minimum and a relative maximum. Again, formal definitions are in the book. Your PowerPoint takes you through guided notes on that, so I'm going to have you read the book and look at that. But essentially, the relative minimum would be those valley points on the graph for an open interval, and the maximum values would be the hill points. And then the last term to look at, and then I'll stop this video and we'll do problems on the next one, are the critical numbers. So this really gets into how do we find these values. So a critical number is a place where the derivative of a function is 0, okay? Now, if we already have said derivative is slope. So when we hit a maximum or minimum value, like if you look at this sine curve that I have drawn, the maximum value and the minimum value, they're occurring at a place where we have slope going from positive to negative, right? Or here negative to positive, so on and so forth. And so the tangent line to this curve at all three of these, what we would say critical points, is 0. So a critical point by definition is a place where the derivative of a function is 0 or undefined. Like if this were an absolute value, you know, if this is a graph and I'm going to graph the absolute value function, this is an undefined point. There's no derivative there, right? It's also a minimum. So critical numbers are places where the derivative is either equal to 0 or it's undefined. And as it turns out, our extreme points, our relative extrema, they are always at critical numbers. So it's a really important thing, and we're going to see this as this chapter kind of goes. It's a really important thing to be able to identify places where the derivative of a function is 0, because something important might be happening there, okay? So I'm going to stop it for now, because that's kind of the conceptual part of this lecture, and then I'll record a second video, because these things take forever to upload, and we'll do some sample problems and talk about the steps to find those things.